So our objective is to compare the average amount of time spent on solving a statistics problem with the neural model of TR84, and the claim is that they're not equal, or it is not equal, to the average amount of time spent on solving a statistics problem using the older model. I'm going to assume that all problems are of the same difficulty, or else it's going to defeat the purpose. Do you agree? So that's an assumption. And we have to use an appropriate test with alpha equals 0.25 to verify the claim by pulling the variance. This is the sample that we have for the new model, and that's the sample that we have for the older model. And you all know how to find the mean standard deviation for each of these samples using the calculator. So go ahead and put these observations in the calculator and tell me what the mean and the standard deviation is. So those are the sample statistics that we obtained using the calculator. So the average time for the new calculator is 7.3 minutes. The standard deviation is 2.6 minutes. We had 10 observations. For the older, it's 10.6. The standard deviation is 3.2, and the sample size is 8. So by the looks of it, do you believe that the averages are different? Yes, but should we just call it quits and move on? We cannot. So even though numerically they are different from a statistical standpoint, they could be the same. So let's verify if it is true. What is a null?
Mu1 equal to mu2.
Mu1 equal to mu2. The alternative,
Mu1's not equal to 2.
and what type of test is this? Two-tailed? Last time I mentioned, if we want to identify the value of mu naught, which is the null value that we are testing for, we could simply move that mu2 to the other side. And that value would be mu naught. The typical value of mu naught is oftentimes 0. But it could be other numbers also. What do I mean by that? So if in the question, if they said the difference in means is not equal to 10, right? Then what do you think mu naught would be? So in the question, it simply says, oh, the claimed mean for mu1 is not equal to mu2. So we end up guessing mu1 not equal to mu2, and then we say, well, the difference in means is not equal to 0, which tells us mu naught is 0. But if the claim were to be, oh, the difference in means is not equal to 7, then mu naught would be 7. So oftentimes it is just 0. Because the rest we can figure it out using a confidence interval. Alpha is 0.25. It is the level of significance and also the probability of type 1 error. Under the null. Or the maximum amount of the probability of type 1 error we are willing to permit is 5%. We want it to be less than 5%. So step 3 is pretty much the data we collected, kind of doing it backwards. Therefore, since we are pooling the variance, we have to find the pooled variance. The pooled variance is simply n1 minus 1 multiplied by s1 squared plus n2 minus 1 multiplied by s2 squared divided by n1 plus n2 minus 2. Do we know the value of n1? n2? Yes. So 10 minus 1 is 9. S1 is 2.6. 8 minus 1 is 7. S2 squared is 3.2 squared. Divided by 10 plus 8 minus 2. Put it on the calculator and tell me what you get. So we found the pooled variance. How do we find the pooled standard deviation?
What do you think, square root of that number?
Take the square root of that number. Which would be 1.47, maybe.
I got 2.88.
Oh, sorry. I forgot part of the 2. So when we have this value, you can always verify if you did it right. The pooled variance, whatever number you find, has to lie between S1 and S2. If it doesn't lie between those two values, you made a mistake somewhere, right? So when you do the homework or the exam, you look at a bunch of options and you can eliminate, just by looking at the answer choices and say, oh, these values do not lie between those two, so they cannot be the answers. Does that make sense? Okay. So we are done with the pooled variance. We would like to know the distribution. Don't believe I can't. So last time the distribution was t, and the degrees of freedom was n1 minus 1, comma, n2 minus 1, and you take the minimum. Here, the distribution is t. With the degrees of freedom equal to n1 plus n2 minus 2. We know n1, it is 10, n2, 8, and 10 plus 8 minus 2 is 16. Step 5, we find this conclusion. There are two ways to find a conclusion. One is the critical value method, the other is the p-value method. And to do either, we need to know the test statistic. What is the test statistic? Remember from last time, I wrote this, the numerator was the exact same term. And in the denominator, we had square root of s1 squared over n1 plus s2 squared over n2. But since we pull the variances together, the denominator is simply sp times square root of 1 over n1 plus 1 over n2. Now, do you see that at the very beginning of the semester I said, well, the process is exactly the same for every single test. The only thing that would change would be the distribution and the way we find the test statistic. The formula is here and there. So x bar, x1 bar minus x2 bar, I believe x1 bar was 7.3, x2 bar was 10.6. What about that difference, mu1 minus mu2? That is the same as the null value, mu naught, right? So what is that mu naught that we had at the very beginning? 0. So the test statistic is negative 2.42. Good. We need to find each of those critical values, but we know if we find one, we could naturally find the other, because one would be the negative of the other. So in order to find the critical value, we need to know the area on either side. What is the area on that table? Go ahead, Anthony.
Is it 0.025?
Is it?
It's half alpha, should
It's half of alpha, so it's 0.025. And on this side, it is the same, so we have 0.025. What function should we use to find the critical value?
What was that?
What function should we use in the calculator to find the critical value? Inverse. So let me put the notation so you would know what to use. So this one would simply be t sub alpha over 2, comma df. Over there it's t sub 1 minus alpha over 2, comma df. And if you use inverse D, 0.025, 16, you will get the left critical value. If you want to find the right critical value, you would do inverse D, 0.975, 16. You can give me either the left one or the right one, it's entirely up to you.
How many decimal places?
2.
2.12.
3.12?
2.12 on the right.
2.12. So we have found the critical values. The one on the right side is 2.12. The one on the left side is negative 2.12. And the rejection region is right over here on the real number line. So where does the critical value fall? The test statistic. The test statistic is negative 2.42. So does it fall in the rejection region? Yes? So it's probably right there. Agreed. So the test statistic falls in the rejection region. Should we reject the null or no? We should reject the null. So what we had thought initially, just by looking at the sample statistics, one was 7.3, the other was 10.6. Initially we thought, oh, they're not the same. But we wanted to see if it is statistically true. It happens to be the case. Are we clear? Okay. And do not forget the absolute value part. So 2 times TCTF area above the absolute value of the test statistic. Well, the test statistic is negative 2.42. What is the absolute value of the test statistic? 2.42. And we want to find that area and multiply it by t. So TCDF, where does the area start? .42. Where does it end? E99. What should be the next term? degrees of freedom, which is 16. So what do we get? Probably about 0.03. Don't forget to multiply it by 2.
Zero point zero two seven seven.
Okay. 0.0277. So based on the data that I collected, if I have to reject the null, or if I did reject the null and concluded that mu1 is not equal to mu2, the probability of type 1 error under the null, based on the evidence that we have, is about 2.77%. So if we did go wrong, the probability of us being wrong is about 2.77%. Is that a lot of probability? No, it's small, so I can reject the null. Not only that, that 2.77% is less than the value of alpha that we set at the very beginning. So we can reject the null and conclude that mu1 is not equal to mu2. Good. Here is a question for you. Do you believe that a 95% confidence interval for the difference in means will contain 0? The answer to this is no. Why? If we look at the test conclusion, mu1 is not equal to mu2. Which would simply imply mu1 minus mu2 is not equal to 0. All I did is I moved that mu2 to the other side. So if I found a confidence interval, that particular interval cannot contain that value 0. I've shown you how to find that interval, so use your calculator, pull the variance, and find the interval, and we can verify if this is true. So I enter the data, so second mode exit, press start, over to tests, and we're trying to perform for this part, we're trying to get an interval. So I'm going to scroll down. And we have to use a t interval. I have the data, I've entered the data in list 1 and list 2. You can ignore the freak part. The confidence level is 0.95, and should we pull, we have to. And that's what we get. Now, does 0 fall in that interval? I'll give you a minute so that you guys can get it. Does 0 fall in that interval? No. A while ago, I said the concept of confidence interval and hypothesis test, they are related. So if you know one, you can easily infer about the other. The advantage of an interval is that it kind of tells you the range where the difference would fall. So in this case, the difference is somewhere between -6 all the way up to -0.437. The same interval, if we did a pooled case, so interval gain, the only difference now is instead of selecting yes, we're going to say no.
Why? Why?
Just to compare the pool case with the not pool case. And you can see it's not that off, right? It's very close in terms of the interval. It's like -6.33 and -0.356. But you do have to notice that the degrees of freedom here is a decimal, right? It's 13.36, and why is it a decimal? Do we do the homework?
Oh, was this, instead of finding the minimum, taking the minimum, this was one of the equations.
Remember that giant formula that we wrote? The DF is computed using that formula. So if on the homework or on the exam, if it asks simply for the DF, if the data is provided, everything is given to you, and it is asking for the DF, use the calculator, right? But if the data is not given, but they want to test you about the formula, then you have to know the formula. But you still don't have to memorize the formula, put that in the cheat sheet. Okay.
That's the Welch's.
Welch's. Yes.
How do you get to the two sample interval thing on the calculator? What is it? Is that?
Start over to test and option 0. So that is the interval, and we can actually perform the entire test using the calculator. So look at all the options 1 through 7, and which one should we pick? If I have to perform a test. Number 4. Right? So we have the data, and the test that we're trying to test is mu1 not equal to mu2. So everything is fine. Switch it over to yes, because we did the pooled case. With me. And that's what we get. What was the test statistic that we got? manually 2.42.
Negative.
Oh, with a negative, thank you. What do we have here? Negative 2.44. The p-value was 0.0277. It's 0.0266. Of the two, which is more accurate calculator because it doesn't do rounding, it goes for 9 decimal places. The same process, instead of calling if we did not pull, we'll get that answer, and that would be the Welch's t-test, right? Just like the Welch's confidence interval, Welch's two-sample t-test. And you can see I'm getting the same GF that I got when I did the confidence interval. And how do we get it? We get it by using that giant formula. And the p-value, again, it's not so different from the value that we got. In the sense, our conclusion did not change. The only time the Welch's t-test would disagree with that approach is when there are significant violations in the assumption. In which case they won't agree. But theoretically speaking, this is more accurate than the other two that we did in class. Does that make sense? Okay.